Hello everyone and welcome to ML Dawn. Previously we talked about entropy and we told you what it means in terms of showing the uncertainty and confusion in a set. And we also showed you that as a decision tree grows and gets trained more and more, the amount of entropy actually decreases. So as you start from the root of the tree and you choose attributes and you choose certain threshold and split and split and split, and until you get to the leaves, you saw that there is a certain pattern which is just a reduction in the entropy from the start to the end. Yeah, but we never said how the decision tree chooses the attributes. So today we're going to talk about that particular factor. So let's go on. So this is our familiar dataset. Again, we got age, height, and salary of different people. And the target feature that we want to learn to predict is whether if we know the age, height, and salary of a person, we could predict whether they're single or not, meaning that if they're in a relationship or not. So we got three attributes here, yeah? Age, height, and salary. Now the question is, how does the decision tree decide which one to select to start the splitting from? There must be some sort of a numeric quantitative metric so the decision tree could figure out which one of these guys is worth more. Is it age? Is it height? Is it salary? And that quantitative metric is called the information gain, or sometimes we show that as some sort of abbreviation as IG. Now, previously we talked about information gain very briefly, and we said that the very building block of information gain is this concept of entropy that we spent the last lecture to dissect. Yeah. Now that we know what entropy is, we want to see what is the relationship between information gain and entropy. But first, let's dig into the very concept of information gain and see how it can be defined mathematically. So, you see this big mathematical formula and you're thinking with yourself, what the hell is S, what the hell is that sigma, V, a member of values of A, blah blah blah. It is just a fancy representation of a very simple concept, okay? Trust me, that's a piece of cake. Information gain, what does it mean? So we're gaining information, yeah? The big question is, which attribute should I choose that would cause the highest information gain? What do I mean by that? Information gain means gaining, let me write it here, gaining more certainty. Well, this should trigger something in your mind, because that could also mean reducing more entropy. For example, let's say the decision tree wants to figure out whether age is a good attribute to choose at the splitting node or not. So in the very beginning, it just says, okay, let's see if age is any good, yeah? And then let's say the decision tree decides that I don't know, like 25 years old is an age that could be a nice threshold. I'm going to tell you how the decision tree chooses this threshold for a continuous variable such as an age, but for now, just bear with me. Let's just say that we chose age and the threshold, the best threshold that we can choose is 25. And then, based on that, the decision tree does two things, okay? Number one, what is the entropy currently? Meaning that before I do anything, before I do any splitting, what is the current entropy on my whole training set, yeah? So if you look at our training set on the left side, we've got a bunch of yeses and a bunch of nos. So we compute the entropy before starting the split. And that is what we call entropy of our set, which is denoted as E of S, yes? And that is what you see here in this formula, this bit right here. What is this? It means entropy, let's just use E to show that, before the split. Yeah? So what is the current entropy that I have right now before I choose any attribute and start any splitting? Okay? And then let's say the decision tree says, okay, let's see how good the attribute age is. And then it chooses 25 as a threshold. Then let's say it does a splitting, yeah? Left hand side, right hand side. So let's say left hand side is true, right hand side is false, yeah? And we end up with two little subtables. In each of them we have a bunch of yeses and a bunch of nos, okay? Now, the question is, how much did the entropy reduce? Okay, that is the main question we want to answer. So we have this nice, in the beginning, this E of S in the very beginning before we did any splitting. And now we want to see how much is the entropy after the split, yeah? So we compute the entropy here, let's call it E of S1, S1 being this little subset over here, and this one would be E of S2, yeah? And then we sum this up together, and that is the sigma that you see on the, in the formula. That is a sigma. But if you notice, we have a sigma there, but we also have this extra bit, this bit over here. It's a fraction. It is a weighting, W-E-I-G-H, weighting mechanism. It means I'm weighting each of the entropies that I've resulted. So the left entropy is going to be weighted. Now, let's say the size of this guy, we show that with, well, this is the absolute size of S1, yeah? And the original set before the splitting has a size as well, and we show that with capital S, yeah? And the right hand side, this subset, S2, has a size as well. We call it S2. And again, we got the size of the original set before the split, yeah? And then we sum these up. This bit and this bit. Now, what is this whole sum? This is the average entropy after the split on age. And it's not just any averaging, okay? Remember, it's a weighted average. We have this weighting by size, okay? I will provide you with a nice numeric example in the next slide. This is just a simple warm-up, yeah? So if you notice, let me just erase this bit to make it a little bit less cluttered. This bit right here, this second half, is all of the sum that I just talked to you about. So the information gain in plain English is a method, is a quantitative method to measure the reduction in entropy. And how do we do that? We say the entropy that I have right now, which is E of S, and the weighted average of the entropy after the split, using my attribute A. Let's say I chose attribute A, whatever it is, and I did the splitting, and I make a nice weighted average across all the resulted subsets after the split. Okay, so before the split minus after the split, whatever I get is the reduction in the entropy if I choose attribute A. Okay, so that is why when we define entropy, we always use an attribute and a set. That is why we have both of those variables in our mathematical formula. So nothing is better than an actual numeric example. So we're going to use a very simple data set to help you understand this concept much better. Let's go. So this is probably the most well-known data set for in decision trees, and this is the data set that I've taken from Tom Mitchell's machine learning book. Very commonly used data set, very nicely formatted. So anyways, the whole idea is that there is this Joe guy who wants to play tennis, yeah? And we want to figure out whether we can predict whether he's going to play or not. And we got day numbers on the left side, and we got 4 attributes about the weather: outlook, temperature, humidity, and wind. And as you can see, for example, for outlook, we have different values, different possible values. So it could be sunny, it could be overcast, it could be rainy. For temperature, it could be mild, hot, or cool. And humidity, we could have high, normal. And for wind, we could have a weak wind, or we could have a strong wind. And then again, the concept that we want to learn is play tennis, which is binary. We could have either no or yes. And all our attributes are discrete. Okay, so remember, the decision tree wants to figure out which one of the attributes is worth more in terms of reducing the entropy. Okay, so if I choose outlook, how much will the entropy reduce from the entropy that I currently have? So it goes without saying that this set on its own already has an entropy that we show with E of S. Okay, and then we choose outlook, temperature, humidity, and wind to reduce this entropy as much as possible. But the question is which attribute to choose. Yeah, and the answer is I'm going to use information gain. But remember, because well, my time is kind of limited to prepare this video, I'm just going to show you how you can compare 2 of these attributes together, and then you get the gist of it. Right, so in our example, we have 9 yeses and 5 nos, and if you go back and review the lecture that we discussed before and compute the entropy of that data set, you realize that the entropy is 0.94, and we set that in a binary classification data set where we have either yes or no's for the ground truth. This is a very high entropy. It means that the confusion is a lot. Yeah. And now we want to see, for example, if the decision tree wants to decide whether humidity is a good attribute to start splitting from, how is it going to measure the information gain? Okay. Now we choose humidity, and now we're going to do the split and figure out what is the entropy after the split. So there we go. We got high and normal for humidity. On the left side, we will get the entropy of 0.98, and on the right side, we get the entropy of 0.59. Now the question is, we know that before the split, the entropy was 0.94, yeah? Over here. Now the question is, how can I combine these 2 entropies to report the entropy after splitting on the attribute humidity? And that was when we talked about information gain. So let's see how it can be computed. There we go. So as we saw before, this guy over here is E of S that we've seen before, and this part on the right hand side is how we are combining our two entropies, meaning this guy and this guy, to report the entropy after the split. And the main thing that to notice here is that, well, for the one on the left side we've got 3 yes and 4 no's, yeah? Hence we've got the 7 over here. And for the one on the right hand side we've got again 6 yeses and 1 no. And then again that results in 7 here. And the denominator is 14 for both of them. So why is it 14? Because the size of S over here is 9 plus 5, 14. Okay, so what does this weight really tell us? What does this 7 over 14 tells us? So this kind of tells you that, yes, if we use humidity, and if we look at the right hand side of the resulted subset, which has 6 yeses and 1 no's, we learned that, okay, the entropy would be 0.59, yeah, and this 7 over 14 tells us about the proportional size of the resulted subset. So this kind of gives us some intuition about the size of the dataset that has 0.59 entropy, okay? I'm going to tell you why this size is important later on, but let's just focus on how you can mathematically compute all of these, and then I'm going to explain to you why do we even bother with these averaging. What does this extra information about the size of these little two subsets would give us? But let's not focus on that for now. We can choose another attribute just to make sure you've got this. Right, so let's say we want to measure the quality of the attribute wind. Again, we have no yeses and 5 no's in the beginning, and the entropy is 0.94, and wind could be either weak or strong. On the left side we got 6 yeses and 2 no's, and on the right side we'll get 3 yeses and 2 no's. So you can see that this is the state of absolute disaster over here. The entropy is 1. It is absolutely chaotic and confused. Okay. On the left hand side, however, the entropy is 0.81. So if we want to compute the information gain, we got the entropy before the split and the entropy after the split. So this is the entropy on the right hand side, this is the entropy on the left hand side, and we got the weighted happening here. Again, we know that the size of our set before the split is 14. Yeah, meaning that we have 14 examples in our set S. Yeah, so we use that 14 and compute these little weights. Yeah, so we get on the left hand side 8 instances, hence we've got this little 8 over here, and on the right hand side we've got 6 instances, hence the 6 over here, and both of them share the same denominator, which is 14, which is the size of the original set. The question is that I have for you, the information gain for humidity is 0.15, yeah, and the information gain for the wind is 0.04. My question for you, which attribute will the decision tree choose if it had to choose from either of these? Which one would be a better attribute to start the splitting from? Of course, because information gain tells us how much the entropy will reduce if we choose a particular attribute, we can see that for humidity we have a much more reduction in entropy compared to the wind. So humidity is a better attribute if it were to be compared to the wind. Then again, there are other attributes out there, but I simply don't have the time to go over all of them, but you got the gist of it. So which attribute has given us more certainty and more reduction in entropy? And we saw that humidity did the job far better than the wind. Now, what if we had continuous attributes, meaning that we don't the values are not nicely behaved like what we saw over here. So Outlook can have only 3 values. Temperature could have only, again, 3 values. Humidity only 2 values, and wind only again 2 values. What if our attributes were continuous? What will change? And so in our previous example that we talked about in the previous lectures, age, height, and salary, well, they're continuous. Yeah, your age could be 25 years and 3 months. Your height could be 182.7. Yeah, so each of these attributes could have any type of value. And if you look at the decision tree that has been constructed, well, I've coded that in Python, and this is the output of the program. You can see that the decision tree has chosen salary, yeah, and get this is the tricky part, yeah. When it comes to a continuous attribute, the main question is, how the hell did this decision tree come up with this threshold, 2,800? Or here for height, how did it choose this threshold of 169.0? Well, yeah, what is the logic? Because if you can come up with a mechanism to come up with a nice threshold, then the rest is a piece of cake, right? You can just split your data set. Okay, which part of my data set has salary less than 2,800 and which part has not a salary less than 2,800, and the rest is more or less the same. But the question is how this thresholding works. Thresholding, a notorious topic in every computer science research area. So let me just tell you how it works in decision trees. So consider this age on the left side, yeah? We got 25, 40, 18 years old, blah, 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 all of that. The way decision tree chooses the threshold is like the following. First, it sorts the values. So we sort the value nicely from the lowest to the highest, and we get to this point. And then it computes the midpoint between every pair in this column, meaning that we've got 17 and 18, yeah? If I look at the midpoint of these two, the midpoint is 17.5. And then again, be careful, we're not going to jump too far down. Immediately 18 and 25, the midpoint is 21.5, so on and so forth. So for every possible pair, we just slide one by one and we compute the midpoints. So we get to this particular column. These are called the candidate thresholds for the attribute age. So then what the decision tree does, it uses all these possible thresholds and computes the information gain for each one of these thresholds. Okay, so if it does so, it will get all these information gains on the right hand side. For example, if we use 17.5 years old for age, okay, and we start to do the splitting. So if we use age and we choose this particular threshold 17.5, what it does is it considers this threshold, and then it considers these two cases, true and false, and it gets the entropy over here, it gets the entropy over here, average them, it will make an average, the weighted average, and then computes the information gain, and this guy right here is the result. Information gain 1. Same story for this threshold, which results in this information gain 2. For the third threshold, the third information gain, fourth threshold, fourth information gain, so on and so forth until we get to the end of our list. And what we get at the end of all this is this nice column of resulted threshold. And what we get at the very end, and what we get at the very end is this nice column of information gains. okay? And then the question is, which information gain is the highest? Let's say, for example, information gain 8 is the highest, meaning that this is the highest reduction of the entropy. Yeah? And the corresponding threshold for that is 45. So these are pair. Remember, these two are pair. Yeah? So then what the decision tree knows is that if it chooses age for the splitting, the best information gain that it can get out of it is the value for information gain 8. Okay? So this is the quality of the attribute age. It does the same thing with every other continuous attribute in the table. And then it chooses the attribute that has the highest information gain for the actual splitting and growing the tree. I hope that it makes sense. It's actually very simple. So the only difference was a mechanism to come up with a threshold to do the splitting. We're looking for the optimal splitting threshold, basically. So the final question that I've seen people ask a lot, and there are not many good sources out there, at least I couldn't lay my hands on. So after a little bit of research, I came up with this following example that I think captures this the answer to this question. Why do we do a weighted average to compute information gain? Okay, in order to simplify this example, let's say that we've got only 2 classes in our training set, meaning that it's a binary classification case, and let's say we are basically torn between 2 attributes, A1 and A2. We want to figure out which one is a better attribute to do splitting on. And then to make it more easier, let's say that our attributes are binary and categorical, meaning that each one has exactly 2 possible values. And now the question is, which attribute would give us more information gain, meaning that which attribute would give us more reduction in entropy and would reduce the uncertainty more. Right, so let's say before we do any splitting, the size of our data set is 1000 and the entropy of our set is E. Let's show it with E, okay? Now we got A1 and A2, okay? If we choose A1 for splitting, we will get 2 possible subsets, SV1 and SV2. On the left side, we'll get a huge set, 990 instances, but the entropy is 0, meaning that this is indeed a leaf. Okay, very nice split actually. But on the right side, we get a small set, only 10 instances, but the entropy is huge. It is 1, okay, the maximum possible entropy. But if we use attribute A2, on the left side we get a small set, okay, but then again entropy is 0, meaning that this is a leaf. On the right hand side, however, we get a huge, indeed huge subset, and the entropy is 1. So the confusion is just absolutely ridiculous. So the question is, if we do the weighting average, and if we do not the weighted average, how would the result of the information gain change? Now, and we want to see whether this weighting thing would give us an idea to choose A1 over A2 or the other way around. Let's see how it works. So this is the case with the unweighted average of entropies. Okay, so this is the case where we just average the entropies the way we would average any numbers, any set of numbers. So we get 2 numbers, so we just sum them up and then divide them by 2. Okay, so for information gain on the attribute A1, we get the entropy before doing the split, which is our E. So in both cases we have E. And in order to combine the entropies after the split, we get 0 and 1, we sum them up and divide them by 2, which is exactly the same case in both cases A1 and A2. And as you can see, the result of this is 0.5, and the result of this is 0.5, and the final result is e minus 0.5 and e minus 0.5. So the information gain seem to be equal. Yeah, so this suggests that A1 and A2 are worth the same. But hold on a minute. I mean, you don't need mathematical derivation to figure this out. Here we've got a major disadvantage. We have a huge set with a huge entropy. This is terrible, yeah? But when we are not considering the size, this huge size over here, the information gain is basically suggesting that these two are the same, but we know that they're not. Let's see if weighting these averages by the sizes of the resulted subsets would make a change. Let's see. Yes, so look at here. We got again E as the case before, that is before the split. Again, we have entropy 0, entropy 1, entropy 0, entropy 1 for both A1 and A2. But look at here. We got the, on the left-hand side, for attribute 1, we've got 990 elements, and that's divided by 1000 because the size of the original set is 1000. And the right-hand side, we've got 10. But down there, look, we got 10 over 1000 and 990 over 1000. Look, this will play a role over here. This is considering the size of huge subset that is hugely confused. Okay, now if you look at this, we get 8 minus 0.01 for attribute A1, and we get E minus 0.99. Okay, so this suggests that A1 is worth more, and that is indeed the case because this one is a larger number. Yes, and that actually makes sense. If we split on A1, we get a huge set with 0 entropy. If we split on A2, we get a huge set with the highest amount of entropy, highest amount of confusion. So as you can see, this idea of weighting by the sizes of the resulted subsets actually plays an absolutely crucial role. So in order to summarize, weighting by the size of the subsets would suggest two main ideas. Number one, a split that results in big impure subsets is a bad split. Okay? By impure, I mean confused, I mean high entropy. But a split resulting in big and pure subsets is good. So this idea, big impure and big pure, is the one that we can address with using the weighted average. Otherwise, we will not be considering the sizes, and we'll counter the disaster that you saw earlier. Right, that was a very exciting video. I really enjoyed it myself, and I do hope that you enjoyed it as well. So we talked about information gain, and we said that how we can compute the value of an attribute in our data set and determine which attribute to choose to do the splitting. And we said that that numeric and quantitative metric is called the information gain. And we covered the cases where we got a discrete set of attributes and a continuous set of attributes. Now, in the next video, we're going to talk about some common issues with decision trees. One of the most important cases with decision trees is the case of overfitting, where we talk about pruning and similar stuff like that. I don't want to digress into that now. But for now, I hope that this has been informative for you. So if you want to follow us on Facebook, Twitter, or LinkedIn, the links are posted in the description to this video. Also, if you're interested to know more about the detail about this particular video, the link to the blog post of ML Done has been posted in the description as well. In the meantime, take care of yourselves and see you in the next talk. Bye.